I want to start today with something that is, well, it's basically a minor miracle.
Oh, yeah.
The fact that you and I are sitting here and we're just making these weird little noises with our mouths.
Pushing air around.
Exactly. We're just creating vibrations, and somehow the listener is decoding those vibrations into, complex thoughts instantly.
It really is the closest thing we have to actual telepathy. A thought goes from your brain, gets encoded, and just pops up in someone else's.
But here's the catch, and this is what we're really digging into today. The system is so fragile. If I say, John visited Mary, everyone gets it. Simple.
Totally clear. A specific event.
But if I just swap two words, Mary visited John, the entire reality flips.
Right.
The words are the same, the ingredients haven't changed, but the recipe has.
And that recipe, that's what we're diving into. The invisible scaffolding of language. It's called syntax.
And we are basing this deep dive on Chapter 4 of Ronald M. Kaplan's Syntax, Concepts, Representations, and Formalisms. And I have to say, when I hear syntax, I still think of my old English teacher, getting mad about a split infinitive.
Right.
But this source isn't about that at all, is it?
Not in the slightest. Kaplan isn't telling you where to put a comma. This is more like an engineering manual for how meaning gets built.
Okay.
Our mission today is to figure out the sort of mathematical rules that let a brain or a computer take a flat string of noises and turn it into a structured, logical idea.
How we get from the sound to the meaning.
Exactly.
So let's start with that meaning side. The source uses this phrase that, I'll be honest, sounds terrifyingly academic.
I think I know the one you mean.
Semantic predicate-argument relation. I mean, I almost closed the book right there.
Yeah, but bear with me, because it's actually really intuitive. It's just the math of what happened.
Okay.
If you strip away all the English, the raw logic of John visited Mary has two parts. You've got an action, and you've got participants.
Right. The action is visiting, and the participants are John and Mary.
Exactly. So a logician or a programmer would write that as visit, John, Mary.
Ah.
The visit part is the predicate. That's the main event. And John and Mary are the arguments you plug into it.
Okay, that makes sense. So syntax is just the problem of mapping the sounds we hear onto that formula.
That's the whole game.
And in English, it seems like we do that almost entirely with word order, subject, verb, object.
English is incredibly rigid that way. Your position in the sentence defines your role. If you mess it up like, visited Mary John,
You get the dreaded asterisk.
you get the dreaded asterisk. In linguistics, that asterisk means this is broken. This is a system crash.
But the reading points out that this obsession with order, it isn't some universal law of language.
Not at all.
That was a real check your English bias moment for me. The book uses Japanese as a counterexample.
It's a perfect one.
Yep.
If English is a position game, Japanese more of a tag game. It uses particles.
What, like little sticky notes on the words?
That's a great way to put it. They're like little badges that say what your job is.
So instead of having to sit in the subject chair at the front, you just wear a subject name tag.
You got it. In Japanese, the particle ge is the subject badge. The particle o is the object badge. So you can say, John Go Mario visited.
Okay.
Or you can completely scramble it and say, Mario John Go visited.
And because John is still wearing that gay badge, we know he's the one doing the visiting, even at the end of the sentence.
Exactly. Both versions map back to the exact same formula.
Hmm.
Visit, John, Mary. So syntax isn't just about order, it's about identification.
Wow. But we don't just speak in simple names. We say really complex stuff. How does that scale up?
We group things. This is the idea of constituents. The chunks. Take a sentence like, the man from the school visited the young girl.
Okay.
If I ask you for the subject, you might just say, man.
Yeah, that's my instinct.
But you can't replace just man with he. You can't say the he from the school.
Right, that sounds terrible. It has to be the whole thing.
The whole package. The subject is the entire chunk. The man from the school. That's a noun phrase.
So I'm picturing these boxes inside of boxes. The verb visited doesn't care about the word man. It just sees this big box labeled subject doing the action.
That hierarchy is absolutely crucial. But here's a kicker. Sometimes the boxes aren't labeled clearly.
Oh.
And that leads to one of the biggest headaches for linguists and for AI, structural ambiguity.
This is the man with the flag example. I spent way too long puzzling over this one.
It's a classic for a reason. It perfectly exposes the potential flaws in the system.
So the sentence is, the man from the school with the flag visited Mary. Help me map the boxes here. Who has the flag?
Well, what does your gut tell you? What do you see in your head?
I see the man and he's holding a flag. Maybe he's in a color guard or something.
Okay, that's a perfectly valid reading. In that case, the little phrase with the flag is packaged inside the bigger box with the man. It's modifying him.
But syntax lets you do it another way.
It does.
The school could have the flag. The man from the school with the flag.
Exactly. In that version, the flag box is tucked inside the school box. The words are identical. The order is identical. But the hidden structure, the grouping, is totally different.
And that changes reality.
Yeah.
One guy is waving a flag, the other just comes from a patriotic school.
And imagine a computer trying to parse that. With no context, both options are mathematically perfect. It's stuck.
It gets even crazier with agreement. The text used the flying planes example.
Flying planes can be dangerous.
Yeah, and that's ambiguous too. Is it the act of flying that's dangerous, or are the planes themselves dangerous?
Right. But watch how syntax can force you to choose just by using agreement. If I say flying planes is dangerous with a singular verb,
Then the subject has to be flying. The activity, like the act of flying planes is dangerous.
correct. But if I say flying planes are dangerous, plural verb.
Ah, then it's the planes. The machines themselves are dangerous.
This shows what we call syntactic dependency. There's this invisible wire connecting the verb to its subject, and they have to agree on features like number singular or plural.
So we've got these chunks, ambiguity, these invisible wires. The second half of the chapter felt like a history of scientists trying to build a machine that could handle all this.
Yeah, it's the evolution of the science. You start with a simple model, you find where it breaks, and you build something better.
Let's walk through that Hall of Fame. Model number 1, the finite state machine.
The simplest idea. It's just a flowchart. You start at the beginning, you see the word the, an arrow points you to noun. You see cat, an arrow points to verb.
It's like a bead on a string. One word just leads to the next.
It is. And it's fast and computationally cheap. But it has a fatal flaw.
It has no memory.
Almost none. Remember that dependency wire?
Yeah.
It works fine if the words are right next to each other. The cat sits. It sees cat, singular, then immediately sits, singular. No problem.
But what if you put a big sandwich in the middle? The cat that chased the mouse that ate the cheese sits.
Exactly. By the time the machine gets through the mouse and the cheese, it's completely forgotten that the original subject, cat, was singular.
It gets distracted by the last thing it heard.
It can't handle that kind of embedding stuff inside of other stuff. It just crashes on complex sentences.
Okay, so the flowchart is out. Enter model number 2. Context-free phrase structure grammars, or CFGs, the tree model.
Yes. And this was a huge leap forward. Instead of a flat chain, you use these rewriting rules, like sentence, noun, phrase plus verb phrase, to build a hierarchy, a tree.
And its superpower is recursion.
Right. A noun phrase can contain another phrase, which can contain another phrase.
The house on the street in the town, you can just keep going.
You can. And trees handle that nesting perfectly. They map those boxes within boxes we talked about. The memory problem is solved.
But the text says CFGs have their own dirty little secret. They're terrible with that agreement stuff.
They really are. A basic CFG rule just says, put a noun phrase here. It doesn't check if that noun phrase is singular or plural.
So how do you stop it from saying something like, the dogs runs?
In a pure CFG, you have to cheat. You duplicate all your rules.
Wait, really?
You have to make one rule. Sentence, plural, noun phrase, plus singular verb. And a totally separate rule. Sentence, plural noun phrase, plus plural verb.
That sounds horribly inefficient.
It's a nightmare. Now add person, tense, gender. You end up with thousands of rules just to say these two words should match. It's called a rule explosion.
Okay, so trees are great for structure, but bad for the details. Which brings us to the rock star of linguistics, Noam Chomsky.
In transformational grammar, the revolution.
Right.
Chomsky basically said, we're looking at this all wrong. There isn't one structure, there are two.
Deep structure and surface structure.
Exactly. Deep structure is the pure logical meaning. John visited Mary. Surface structure is what you actually say.
And the transformation is the bridge between them.
It's literally a movement operation. Take the passive sentence. Mary was visited by John. The deep structure is still the simple John visited Mary. But a transformation rule picks Mary up, moves her to the front, and shoves John to the back with the word by.
It's like rearranging the furniture in a room. The pieces are the same, but the layout is different.
That's a perfect analogy.
Right.
And it solves so much. It explained why two very different sentences can mean the same thing.
But here's what surprised me. The computer scientists building AI, they kind of hated it. Why? It sounds so elegant.
It's elegant for generating speech. for going from a thought to a sentence. But computers usually have to do the reverse. They hear the sentence and have to figure out the thought.
I see. It's hard to run the movie backwards.
Incredibly hard. It's like I give you a scrambled egg, the surface sentence, and ask you to figure out exactly how it was unscrambled back into a raw egg. There are just too many possibilities. It was a computational nightmare for parsing.
So great for theory, terrible for building Siri.
In a nutshell, yeah.
Which brings us to the computational turn. The engineers needed something that actually worked on a machine. And this is where the author, Kaplan, comes into the story with LFG.
Lexical functional grammar. And this is really where things start to click for modern tech.
Right. LFG says we process two things at once, in parallel.
The C structure and the F structure.
Okay, what are those?
The C structure, or constituent structure, is just the tree. It handles word order, the phrases, all the surface stuff.
And the F structure.
That's the functional structure. Think of it like a checklist of attributes. Subject, object, tense, number. It doesn't care about the order. It just cares about the roles.
So how do they talk to each other? How does this solve the rule explosion?
Through constraints. This is the genius part. Attached to the tree, you have little equations. So under the noun phrase spot, you might have a note that says, whatever lands here, put its information into the subject slot on the checklist.
Head under the verb.
You might have a constraint that says, hey, check the checklist. The thing in the subject slot must be plural.
So instead of a million rules, you just have a bouncer at the door checking IDs.
Exactly. The system builds both structures at the same time. If the features from the tree can unify with the constraints on the checklist, the sentence passes. If there's a clash,
it's ungrammatical, a crash.
And it's so much more efficient.
The book also mentions HPSG briefly.
Head-driven phrase, structure grammar. A similar idea, using these complex feature checklists, but it organizes them using inheritance, kind of like an object-oriented programming. It's very powerful.
But then, after all this talk about trees and features, the chapter ends with a plot twist, dependency grammar, which apparently is what a lot of modern tech, like Google, actually uses.
Yeah, dependency grammar is an old idea that has made a huge comeback in the age of machine learning.
And it basically says, forget the phrases, forget the boxes, just draw arrows between the words.
It strips it all down. In John Visited Mary, you don't build a tree. You just draw an arrow from visited to John and label it subject. An arrow from visited to Mary labeled object.
That's so direct.
It is. It ignores all the abstract stuff like noun phrases and just asks which word is the boss of which other word.
And computers love this because
it maps directly to the meaning. If you have that arrow, you immediately have your visit John Mary formula. You don't have to climb down some complex tree to find it. And it's way easier to train a machine learning model on those simple direct links.
Okay, so let me try to recap this journey. We started with John visited Mary.
Right.
We found we need an invisible structure. We tried simple flowcharts, but they had no memory.
The sandwich problem.
We tried trees, but they exploded with too many rules to handle the details. We tried Chomsky's transformations, which were brilliant, but impossible to run in reverse.
Parsing nightmare.
And so we ended up with these modern systems, either constraint-based ones like LFG that have parallel structures, or dependency models that just strip it down to the arrows.
All of them just trying to solve that one puzzle.
Yeah.
How to be the interface between the flat line of sound and the deep hierarchy of meaning.
The interface. I like that. Syntax isn't the meaning, it's the API that connects to it.
That's a great way to put it.
But this leaves me with this one big question. We've built these models, LFG, dependency grammar, and they work on our computers. But which one is real?
What do you mean by real?
I mean, in my brain right now as I'm talking, am I actually building a little fist structure? Am I drawing dependency arrows between my neurons?
Or are we just building models that happen to get the same answer, but use a totally different process?
Yes.
That is the million-dollar question in cognitive science. We know a lot of these formalisms are, in some ways, mathematically equivalent. You can translate a tree into dependencies, but does the brain actually do that?
Because it really feels like we don't have a little Chomsky in our heads moving furniture around.
Probably not.
Yeah.
A lot of thinking now is that our brains might be much more probabilistic. Less about rigid rules and constraints, and more about a massive fluid network of statistical patterns. We might just be predicting the most likely structure, not building it from a blueprint.
So the AI we're building might actually be more rigid and structured than our own minds.
It's very possible. We're building machines that follow the rules of the grammar book perfectly, while we humans are just really, really good pattern matchers who happen to get it right most of the time.
That is a truly humbling thought. We're teaching the car how to follow the map while we're just jaywalking and somehow ending up at the right destination.
And yet, we get there.
We do. Thank you so much for walking us through this. I'm going to be seeing invisible brackets everywhere now.
It's a blessing and a curse.
Thanks for listening to this deep dive. We'll catch you next time.